Okay, to start us out, since we're talking about continuity, I thought I would throw up a definition of continuity. And, I mean, this is really kind of mathy and wordy. It says, assume that f of x is defined on an open interval. So we have a function, and it's defined. And it contains c. C is just on this graph somewhere. Okay, there's an x value that is c. Then f is continuous at x equals c if this is true. Now what does this all mean right here? This means the limit as you approach c is going to be the same as if you were just to plug c in. I know some of you guys have already been doing that. You just would plug in the number and you would find the answer. Well, that works. Only though when it's continuous. And so that's what we're going to look at today. This says if the limit does not exist or it exists but is not equal to fc, then we say that it has discontinuity. So let's just talk about continuity first. All right, look at this guy right here. This guy is discontinuous, he's discontinuous, he's discontinuous, he's discontinuous. You know that a function is discontinuous if you have to lift your pencil up at all when you're drawing a line. I mean, I suppose you don't really have to lift up your pencil when you draw the circle, but technically there's a hole right there, right? And so you would stop, put a dot right there, then come back, and then finish. Okay, this is discontinuous. All of these are discontinuous. Now this top one, though, is a special discontinuity. This is called a removable discontinuity. And that's important because the limit exists for this. Now we've already looked at limits, so you guys should be able to answer that question. If this is f of x, does the limit exist? Oops. If I'm approaching 2? X approaches 2 of f of x. Yes. What does it equal? It equals 5, right? Because it's approaching it to right there. It's approaching it to right there. But you guys know something else about functions. If I went, what does f of 2 equal? What would you guys tell me? It equals 10. That's why that dot's right there. If I plug in 2, I'm going to get 10. Does this limit equal when I plug it in? No, it doesn't. Because this is discontinuous. Now, if they did equal each other, then it's continuous. All right, you don't have to lift up your pencil when you draw a line. It's kind of funny. I'm saying the same thing, but a different way a bunch of times. Okay, but we're trying to learn about what continuous means. So these are the same graphs. I just moved them up a little bit. These are discontinuous as a whole. However, you can say that these have left side or right side continuity, and that depends on if there's a closed dot. See, this one is right side continuous. And the reason why it's right side continuous is because I could take the limit as we approach 2 from the right. We'll call it f of x. And what would I get? Okay, if this is our f of x function right here, if I'm approaching 2 from the left, I would get a y value, right? We'll call it y sub 1. We'll call this one y sub 2. Okay? So as I'm approaching 2 from the right-hand side, which is plus, I get y sub 1, right? Now, because I can say f of 2 equals y sub 1 also, if I plug in 2, I get y sub 1, right? I do not get y sub 2. I get y sub 1. Because they equal each other, we say it's right side continuous, or right continuous at x equals 2. Is this left continuous? No, because that approaches a different y value, and it doesn't equal y sub 1, just like this one does right here. So you can have left side or right side continuity. Okay. Now this function as a whole is discontinuous, but because it has solid dots on these lines, they can be considered continuous on one side. So this one's left side continuous. It is not right side continuous. This one is neither right side or left side continuous because it has a removable discontinuity. It's off of the lines. Okay, so that's just some quick vocabulary, and here's the formal thing of what I just said. Go ahead and take a pause on that and copy it if you're watching the vid, or if you guys are copying it, you're probably just gonna have to go to the book because I'm trying to go fast here. All right, let's graph this dude. Look at this bad man pajama. You guys remember Piecewise? Yeah, it's not that bad. Here, check it out. Especially the one I made right here. Actually, I copied this one from the book. But these are really simple functions. You guys see those functions? You guys know what those functions are? Like if I went y equals x. You guys know how to graph that. You guys know how to graph y equals 3 and y equals x. That's all these are right here. Okay, these define the intervals on which you graph those functions. That's a quick review for piecewise. And let's see, we have two major points. We have 1 right here, and we have 3. So for the first interval, that's this interval right here. That's x is less than 1. All right, I'm going to graph the x equals function. So this function right here, well, if I plug in 0, I get 0. If I plug in -1, I get -1. If I plug in -2, I get -2, -2, -2. And then if I plug in -3, I get -3. Hey, yeah, we just get this straight, like, perfectly slanted line. If I plug in 1/2, what would I get? I get 1/2. Right? If I plugged in 1, what would I get? Oh, you got my trick. Okay, I can't plug in 1. Why can't I plug in 1? Because it says as the x has to be less than 1. 1 is not less than 1. So we're going to put a circle right here, to say we cannot plug in 1. And so this interval is done. Let's do the next one. The next one is right here. It's between 1 and 3. And so that's this one. Let me circle that one in purple so we know we're graphing it. Y equals 3. You guys know how to graph y equals 3? Horizontal line right at 3. So I'm going to go up to 3. So it's 1, 2, 3, and just draw my horizontal line right here. Now I'm going to put a solid dot there and a solid dot there because it says equal to. That means I can plug in the 3 and the 1 to this function, and I should get dots. And then for the rest of it, anything that's greater than 3 is back to the other function. So we're going to continue where we left off. We'll call this one red, and we're going to go, if I plug in 3, I get 3. If I plug in 4, I get 4. If I plug in 5, I get 5.
Would you not get a 3 for 3?
Yeah, you're right. I wouldn't be able to plug in 3 because it doesn't say equal to. However, in this situation, the other function plugs in 3 and gives me 3 also. So it's okay to put a solid dot right there because the other one fills it in. All right, so discuss the continuity of this. Well, is the whole function continuous? No, the whole function is not continuous because we have a jump right here. There's a gap. I would have to lift my pencil to write this. Now, is it continuous, though, in some spots?
Yes.
Yes, it is. Like, it's continuous right here. Like, all of that, it's all continuous. It's continuous down here. That's all continuous. Let's just talk about 1 right now. If I was approaching 1 for this function, let's say the limit as x approaches 1 of f of x. Does that limit exist? If I go to the left, and then if I come from the right, do they approach the same limit?
No.
No, so this one does not exist because it has a jump discontinuity. But if I changed it, if I said the limit as x approaches 1 from the left-hand side, what would that equal? From the left-hand side. So we're coming this way in the line. That means we're coming up this way. What are we approaching? What y value are we approaching when we get to 1? Yeah, 1. So this equals 1. But what does f of x or f of 1 equal?
3.
It equals 3. So is it left side continuous? Because we're coming from the left? No, it's not left side continuous. If we came from the right, though, if I came from the right, if I approach x from the right, if I'm coming this way on the x-axis and I'm coming this way on the function, what's it approaching? 3. Okay, look. Is it right side continuous? Mm-hmm. Yes. Why? Because they're equal. Okay, and also you can just say, oh, it has a solid dot right there. Okay, that's saying the same thing. So we discussed the continuity a little bit here. The most important part is where it's jumped. But let's look at some other examples.